Hi guys, so now we shall look at JK flip-flops. JK flip-flops are another kind of memory circuit just like the SR flip-flop, and its aim is to replace the SR flip-flop by fixing its mistakes or fixing its problems, particularly the fault condition and the race condition. Now, JK from this name refers to Jack Kibley, and Jack Kibley is an American electronic engineer, and he's an inventor, and he was of course responsible for the invention of the JK flip-flop, and he was awarded the Nobel Prize partly for his invention or contribution to the invention of the integrated circuit. So a lot of the computers that we have today and use today are a direct result of his work. And you see a picture of the gentleman on the left. That's Jack Kibley. Now, although the name is JK, it doesn't just pertain to his name, it also pertains to the inputs that we pass into this circuit. So if you look at this circuit, it's incomplete because I want to complete it with you. This circuit has three inputs. J, which is similar to the set input of the SR latch. There's another input called K, which is similar to the reset latch, the set reset latch reset input. So J is similar to set and K is similar to reset. And we also have a new input called CLK. CLK refers to a clock or a clock input. Clocks are basically circuits in our computers that tick at regular time intervals. Basically, it's like our clocks at home, like our grandfather clock, for example, that's ticking every second or every minute, however the frequency might be. But in the computer, of course, these clocks are ticking much faster, about 500 or 500,000 times every second, right? And usually the frequency of the clock is given by some megahertz value. So the idea is, not only do we take in a set signal and a reset signal into this circuit, we also take in a clock signal, which is basically a signal that either is 1 or 0 at regular time intervals. And you'll soon realize why this is important. The outputs of this logic gate circuit are Q and Q complement, similar to the SR latch. Q is whatever data it was storing. Q complement is the opposite of whatever data Q was storing. So Q is the memory rather, and Q complement is the opposite of Q. Right, so let's now connect these up because I want to help you guys understand how to connect these up by yourself. So what I'm going to do is I'm going to first draw a line from the J input to the middle of the NAND gate and the K input to the middle of the NAND gate. And then the clock signal also goes into both the NAND gate above and the NAND gate below. So therefore we need to sort of split this. So what I'll do is I'll draw a line like this from the NAND gate, draw one line below and another line below to the NAND gate below. And to denote that this is a junction, I'm going to draw a small circle here that is colored in to say that the wires are splitting. Okay. Now you might be wondering why I left some space above and below in these NAND gates, because there's going to be a third wire coming in, because these NAND gates are no longer just 2 input NAND gates, they are tri-input NAND gates, and we'll see how that works soon. So okay, so part of our work is done, connecting the inputs are done. What else do we need? We need to connect the output of this initial layer of NAND gates to the next layer of NAND gates. So what I'll do is I'll pass in a wire from this NAND gate to the NAND gate in front. From this NAND gate to the NAND gate in front. And let's do the same for the NAND gate below. Okay. And then the rest is pretty simple. The NAND gates that come in front, the second layer of NAND gates, are to be cross-coupled, which means that you are supposed to connect them in a similar fashion to the way that the SR latches NAND gates were connected. So what I'll do is I'll first extend out these outputs to Q and Q complement, and then what I'll do is I'll borrow the signal Q and pass it down as another input to the NAND gate below, and do the same for this as well. Take a copy or take a D route of the Q complement signal and pass that as another input to the NAND gate above. So this part of the SR or JK flip-flop is basically the same as the SR latch. or the SR flip-flop. Let me demarcate these junctions with circles as well. And then you might wonder, okay, is that enough? Not really. There's just one more step. Remember how I told you that these two NAND gates are tri-input NAND gates, which means that it's supposed to take in multiple, or actually 3 inputs, not just 2. Where is the third input coming from? The third input comes from the Q and the Q complement themselves. So what I want to do is I want to take a copy of Q complement. I'm sorry, in this case we'll take a copy of Q, and I'll draw a line down, and I'm going to jump over the Q complement to say that it's not connected to the Q complement. It's just a copy of Q and Q only. I'm going to take this down and move this all the way to the NAND gate below and make that the third input to the NAND gate. And you might wonder, okay, what's the next step we do? The next step we do is basically do the same thing for the Q complement output. So we take Q complement, jump over, and basically pass that signal as the third input to the NAND gate above, right? Okay, let me complete the circuit by drawing the jump over and making this a junction. But yeah, that's all. That's all you need to do with regards to sort of creating this circuit. So you have just 4 NAND gates, and you need to connect them in this form where the J, clock and K connect to the first NAND gate series, the first 2 NAND gates. The clock of course has to duplicate to connect to both the NAND gates, but then you have 2 other NAND gates in front which then cross couple similar to the SR latch, and then you have one of the outputs connecting back to one of the NANDs, and the other output also connect back to one of the other NANDs. That's all. That's all you need to understand with regards to the SR's the JK flip-flops implementation. Now, I told you I'll look into what this tri-input NAND gate looks like, or what it does, right? So let's look into that now. Notice how I've drawn the truth table of a tri-input NAND gate. What I want you guys to think about this is as a simple tri-input AND gate, but it's negation. So the AND gate, regardless of the number of inputs, only outputs 1 if all inputs are 1, right? So if you have A, B and C, regardless of their combinations, Q will only be 1 if A, B and C are 1. That's the only possible combination in which Q is 1. Every other combination Q is not 1, right? So basically that is what happens in the AND gate scenario. Every combination but 1, 1, 1 is 0. But the combination where A, B and C are all 3 ones, the output is 1. So how the NAND gate works is you just take the negation of that, the opposite, the inversion. So you take all the zeros such that they become ones, and then you make the last one a 0. So the final output is a series of ones and a 0 at the end. That's the truth table for the NAND gate. And you might be wondering, okay, why do we have this kind of tri-input NAND gate? Now, of course, the reason here is we need to have 3 inputs. But why do we have 3 inputs here? Now, let's look at this NAND gate. This NAND gate takes in J, the set input, the Q complement input, which is the Q complement from the previous time interval passing in at the current time interval, and we have a clock signal. Now, the idea is, notice that this NAND gate will only output a 1 when J is on, when Q complement is on, and when the clock signal is high. So what that means is, it requires the clock signal to be high in order for any changes to be made to the circuit in front. So what we're sort of doing here is, we are no longer just reliant on Q and the output Q complement and J. We're not just reliant on those 2 things only, which was the case in the SR latch. We were only relying on the set input and whatever the Q complement's input was earlier. Now we are relying on that plus another clock signal. So what that does is, no matter what changes the user might do to the latch in front referring to this circuit in front, none of those changes are persisting unless the clock signal is high. So what we're doing effectively is we're avoiding this sort of race condition from the latch before. The SR latch's race condition is avoided because the clock signal needs to turn on, which happens autonomously, in order for the changes to actually persist within the SR latch or the circled part in front. So it won't store anything besides if the clock signal is high. So even if you make changes to J, or if Q complement is also on, nothing will happen unless the clock signal is high. The same goes on with the K. If you're trying to reset the latch, nothing will happen to the latch until the clock signal actually comes on. So the idea is this latch relies on the clock signal. No matter what changes we make, those changes will only propagate into the latch in front, meaning this part, and it will only be able to store the data when the clock signal is high. In every other occasion, nothing will be stored. So we are having this concept of user input where we are making the changes to J and K, but none of those changes pass through until the clock actually tells the signal or tells the circuit to turn on. The clock is also playing a major role here. So we are preventing race conditions because unless the clock is on, no changes actually propagate into the logic circuit. So taking a look at the clock signal, what it exactly is, like I said, the flip-flop only activates during a high clock signal. So the clock is ticking, and since this is a digital clock, it's ticking 1, 0, 1, 0, 1, 0, so on. So what this idea means is the JK flip-flop only activates when the clock signal is high. So only in these portions where there are ones, the clock signal would propagate through and would result in changes in the JK flip-flop. In every other occasion, that is when the clock signal is 0, no matter what changes we make to the JK flip-flop, those changes won't persist. Those changes will only propagate when the clock signal is high, when it is 1. Alright, okay. So that's about the architecture and sort of how a JK flip-flop attempts to solve the race condition of the SR latch, and also how the JK flip-flop is constructed from just 4 NAND gates. In the next video, we'll take a look at how this latch actually stores data by observing its truth table and the respective solutions to the problems of SR latch itself.